Hello, welcome. Today my plan is to cover Learning Objective 1, Vectors. Before that, I want to show you a few things, how to access OneNote and use that to solve questions and upload to Gradescope possibly. So you can access our class notebook from this link over here or through Microsoft Teams. Go to class notebook on top at the general channel tab. Um, so you can, if you do it from here, you can click in here and it will open it up in a web page. But I do recommend opening it up from the desktop app. So you click on this desktop app and the desktop app will open. Usually that will be taking a while to load, so I opened it up beforehand. Notice here the class notebook that um, the content library contains all the solutions for challenges and the in-class activity, and also put a tab here in collaboration space for student hours. This will in here I will post solutions to sample questions that we work out in the during student hours. Okay, so under here, I created a new page, which you can do easily. And once you create a new page, you can add a printout. So let me do it over here. You add a printout, and so you can upload your challenge PDF in here, and it will show up just like here it did for LO1. Um, and so from here, then you can use a smart pen and figure out the answer. Once you're done with the answer, you go to the right corner here and print and save as a PDF, and then upload to Gradescope. So so let's talk about vectors now. So vectors were originally invented by physicists to describe motion and velocity and various forces that apply on an object and study their movement. So they're very useful for those for simulations. For example, the car racing game that you saw on the in-class activity, or the magic carpet and hoverboard. Those are kind of cool applications of it. We will see a bunch of other applications in the next learning objective. Uh, but I've used vectors in number theory, which I never thought that they're related, but it turns out that they are. And I studied in particular some vector space of power series, and I had to figure out the dimension of that space in order to progress on my research question. So it's surprisingly like how useful they become. And once mathematicians took the idea from physicists and about vectors, they were able to generalize them and think of power series, for example, as vectors, or polynomials as vectors, functions as vectors, and then ask all sorts of interesting questions about them and solve the multitude of other questions using the ideas of vectors. But in this class, right now, we will only focus on the basics. So what is the criteria for success for this learning objective? Well, I can represent vectors in 2 or 3 dimensions as ordered pairs, triples, as arrows, and specified by magnitude and direction. So if you give me a vector in 2D or 3D, you can write it as uh, ordered pair or triple, meaning like in component form. Or you can say in this direction, go 5 miles or something like that. So you can specify the direction and how far you're going. And the direction generally is given by some angle. For example, in 2D, that's kind of easy. You say 30 degrees, 5 units away from the origin, so you can understand how to draw that vector. Um, And oftentimes in navigation, if you're flying a plane or something, that's the easiest way to navigate. You don't say, "Well, go 2 miles east and 3 miles north." That's not usually how you tell a pilot to drive an airplane. So the different representations have different strengths that can be used in various situations. So next thing, you want to be able to give physical examples and illustrate the distinction between a vector and a scalar. So a vector has 2 or 3 components. There is also one-dimensional vectors, but those are just numbers. So you can think of the number line, and then any number on the number line can be thought of as a vectors from the origin, starting at the origin and ending at that point. But similarly, you can do the same for any dimension. If you pick any point in 2D or 3D space and draw the arrow from the origin to that point, you can think of that vector. And going back between like a point, thinking of it as a point and a vector is a quite useful thing to do. So then you need to be able to add and subtract vectors geometrically, which means tip to tail, put them next to each other, or the parallelogram rule. You need to do that symbolically, adding components or subtracting components, and multiply a vector given both geometrically and symbolically by a scalar. So if you're given an arrow in space and I say, well, this is 2 times that arrow, then you make it 2 times as long, or minus the arrow will reverse the direction. If you're given it by numbers, component form, then multiplying by 2 means you're scaling each of the components by 2. And it would also mean the arrow representing it just gets scaled by 2 as well. So you need to kind of have both of this in your mind and be able to move between these two representations. And I can use vectors. I can use properties of vector operations to manipulate vector expressions and apply them to motion questions. So this is an application question. So uh, you need to be able to do stuff with vectors after you're comfortable with these simple rules that underlie vectors. Then how can we use them to do stuff? So sample question. Uh, let me try to solve here the very last question, um, so we can see um, how you can attack something like this on the challenge. So assume you throw a ball forwards with a force F1 of magnitude 20 pounds, while wind is blowing northeast parallel to the surface of the Earth with a force F2 of magnitude 10 pounds. Find the resulting force acting on the ball in component form as well as its magnitude. Assume that all vectors here have 3 dimensions. Okay, so there's a lot to process in here, and usually when I face a story problem, I need to really think think a lot to make sure I understand each of the sentences. And when I was an undergrad, this was especially hard to do as a non-native English speaker. So I remember myself with taking, for example, Calc 2 with a dictionary on my side to translate certain words. Um, but even if you are a native speaker, it is quite hard to process mathematical text. So whenever you read a sentence, try to draw a picture, try to figure out how to represent that information geometrically. So here, assume you throw a ball upwards with a force F1 of magnitude 20 pounds, and I, I notice here we're talking about 3 dimensions, right? So there's a ball is I'm gonna throw it up. Okay, so let me draw that out. And it's 20 pounds, which means the magnitude of this vector is 20 pounds. So this is F1. And while wind is blowing northeast parallel to the surface of the earth with a force F2 of magnitude 10 pounds. So this is going up, but we have north and east. So we have north and east, right? And this is what's going up, 20 pounds. So northeast would be in this direction. Let me use a different color here. So northeast would be 45-degree angle in here. Okay, and that's the wind, and it's blowing parallel to the surface of the earth with a force F2 of magnitude 10 pounds. So this is the length of this arrow is 10. Um, Find the resulting force acting on the ball in component form, as well as its magnitude. Assume that all vectors here have 3 dimensions. Right. Okay. So I think we got there's components form. Let's figure out the components form here for this vector. So F1, what's that vector gonna be? 20 up. It's not moving left and right, so that means 0, 0, 20. And F2, it's only the wind is blowing parallel to the surface of the earth, so there's no height change. That means the third component here is 0. Let me do this in green. And then you're gonna go, well, we need to figure out the x and the y here. This is a 45-degree angle, so projecting here on the x-axis, which is the east direction, and the y direction, this is a right triangle, so 10 times cosine 45 would be the x, and 10 times sine 45 would be the y, and 0 is the height. So then we have F2 is 45 cosine of 45 root 2 over 2. So 10 divided by 2 is 5 root 2. This is also 5 root 2, 0. So we have the components form. Find the resulting force. That's what we need to figure out. So how do we find the resulting force? Well, that's the force that if you put the two together, which means you're adding the two vectors here. So you can use the parallelogram rule here to make sense of that and be like, hey, I'm going to add this up. So you build a parallelogram to go there. Another way you could do this is you could translate the vector F2 up here at the starting at the tip of F1. Right? This is also vector F2. The vectors are independent of coordinates, so you can kind of move them around anywhere you want as long as their shape is the same and the direction is the same. And then you just add the two, okay? So how could we figure out, well, let's see. So we want to find this force in component form. Let's call this F. F is the resulting force, so it's F1 plus F2. Well, since we're given the components here, that's not too hard to do. It's 5 root 2, 5 root 2, and 20. So you're going to add F1 and F2 together. Okay, so we figure out the component and find the magnitude. So to find the magnitude of the vector, you can use the Pythagorean theorem. Why is